Hello everyone and welcome to our module on pressure volume loops. So to understand what a pressure volume loop is, let's start by looking at this graph on the left side of the screen here. Along the x-axis I've shown time, and on the y-axis at the top I've shown the pressure inside the left ventricular cavity as time goes by through the cardiac cycle. So what happens is as the left ventricle contracts, it squeezes the blood in the chamber, driving up the pressure like this. Then eventually the aortic valve opens and blood begins to leave the left ventricle for the aorta, and then the pressure starts to come back down. And this goes on over and over again each time the heart goes through the cardiac cycle. On the bottom on the left, I've shown the left ventricular volume and how that changes over time through the cardiac cycle. So it starts off at some high value when the chamber is filled, but then blood starts to leave and the volume goes down. And then eventually the mitral valve opens and blood begins to come back in and fill the chamber for the next cycle. So if you take each point of volume and each point of pressure at a given time and you plot it like I have done on the right side of the screen here, you get what's known as a pressure volume loop. We have the left ventricular volume along the x-axis, the pressure along the y-axis. Time is not shown, but time is going in a circle like this, okay? The left ventricle is filling with blood, making the volume go up. Then the left ventricle squeezes, driving the pressure up. Then blood leaves and the volume goes back down. And it goes around and around with each cardiac cycle in a left ventricular pressure volume loop. And so in this video, we're going to talk about what the different parts of the pressure volume loop mean and how these loops change for a given heart in certain disease states. So the first thing I want to point out is that there are 2 points in the graph on the left where volume is not changing. There's this one right here between the red lines and this one right here between the green lines. And I've shown where these 2 points are represented on the pressure volume loop over here on the right-hand side. The red area here is where volume is constant, and for volume to be constant, it means the mitral and aortic valves have to be closed so that no blood can enter or leave the left ventricle. And so that's what's happening here. Volume is constant, the valves are closed, but the ventricle is contracting and driving up pressure. And so this part of the pressure volume loop is called isovolumic contraction because there's no change in volume, but the ventricle is contracting. And then this portion over here in green, the pressure is falling. That's because the chamber is relaxing. Once again, the valves are closed. Blood can't get in through the mitral valve or go out through the aortic valve, but the chamber is relaxing, allowing pressure to come down. So that's called isovolumic relaxation. And so these 2 points in a pressure volume loop where the lines are straight are the isovolumic portions that you should know about. Now, I also want to point out this line right here. This straight line right here is called the end systolic pressure volume relationship. And this sort of curved line right here is called the end diastolic pressure volume relationship. These 2 lines are determined by characteristics of the ventricle. So for different ventricles in different states of activity or disease, they could be different. But they're important because they dictate how the ventricle can operate. So when the ventricle fills with blood, it's going to move the volume along this line here, along the end diastolic pressure volume relationship. And when the ventricle pushes blood out through the aortic valve, which we'll talk about in a minute, it does so until the volume falls to this point right here. So these points, this one right here and this one right here, they're being dictated by these 2 lines, and they're going to be important later on when we talk about things that can change those lines and therefore change the shape of the pressure volume loop. Let's talk about what's going on with the valves at different points in time on the pressure volume loop. So shown here is an M on the left side. That's when the mitral valve closes. And when the mitral valve closes on a pressure volume loop, that's always here in the bottom right-hand corner, right before the isovolumic contraction phase starts. When the aortic valve opens, that's when blood is able to leave the left ventricle. So that's going to always occur right here in the top right corner, just before the volume begins to fall, moving down the x-axis because we've opened the aortic valve. When the aortic valve closes on the left, that's going to be right before that flat portion where volume is constant, and that's always going to be in the top left corner of the pressure volume loop. We're then going to enter the phase of isovolumic relaxation where pressure will fall. And then eventually, when the pressure gets low enough, the mitral valve opens, and that's always in the bottom left-hand corner here. And you know that because when the mitral valve opens, the next thing that's going to occur is the volume is going to go up as the left ventricle fills from the left atrium. In the video on heart sounds, I talk about how closure of the mitral valve is a component of S1. So the bottom right-hand corner of the pressure volume loop is where you would expect to hear the first heart sound. Also in the heart sound video, I talk about how when the aortic valve closes, that's a component of S2. So here in the top left corner is where you would expect to hear the second heart sound. Also remember, as I said, that even though time's not shown on the pressure volume loop, time is moving in a circle in this direction, in a counterclockwise direction. So the green portion here, from here to here, that's all diastole. That's when the left ventricle is relaxing and then filling with blood. And then the red portion here and over to this side is systole. That's when the left ventricle is contracting, first isovolumic contraction, followed by contraction that pushes blood out into the aorta, and therefore the volume falls going in this direction. And so if you understand that, it should be fairly easy to understand that since this point right here represents the end of diastole, the volume along the x-axis at this point is the end diastolic volume, and the pressure along the y-axis is the end diastolic pressure. And so in a board question, they might give you actual numbers along the x and y-axis and ask you for the end diastolic volume or end diastolic pressure, and you can identify those points easily from a pressure volume loop. By the same logic, this point right here represents the end of systole, and therefore this is the end systolic pressure, and this is the end systolic volume. And as you may recall, stroke volume is equal to the difference between the end diastolic volume minus the end systolic volume. That's how we calculate stroke volume. And so you can actually identify the stroke volume from a pressure volume loop. It's the difference between these two volumes here along the x-axis. And we'll talk more about that in just a second. Let me also point out that this point right here represents the preload of the left ventricle. I talk about preload in detail in the cardiac physiology video, but what you can see in this pressure volume loop is that the volume, which is along the x-axis, goes up until it reaches this point right here, and therefore that point represents the maximum volume inside the left ventricular cavity, and therefore the preload on the left ventricle. You should also know that this point up here represents the afterload. Afterload are the forces that resist blood leaving the left ventricle, and so basically the ventricle is going to contract and drive the pressure up until the pressures become high enough to open the aortic valve, and that pressure where the aortic valve opens and blood starts to leave the chamber, that represents the afterload. You should also know that the width of the pressure volume loop represents the stroke volume. Volume is going up until it reaches this point here, then it's falling down until it reaches this point here, and so the difference between those 2 points represents the stroke volume. And that's a super helpful thing to know when you're answering questions about pressure volume loops, because they'll often show you 2 loops and ask you which one represents the left ventricle with a higher stroke volume, and it's always going to be the wider pressure volume loop. Okay, so now that we understand what a pressure volume loop is and what some of the important points on pressure volume loops represent, for the rest of this video, I'm going to talk about how pressure volume loops change when you modify certain important parameters. These are the kinds of things they like to ask you on physiology exams and step exams. So we'll talk about what happens when you change preload or afterload, when you change contractility or compliance. Now keep in mind, in reality, all these things are interrelated. So for example, when you increase the preload, you stretch the myocytes, and that raises contractility by the Frank-Starling mechanism. But in these examples I'm going to show you in the next few slides, we're trying to consider what would happen if you modified preload in isolation and there was no subsequent change to contractility. That's the way to think about these pressure volume loop type problems. So shown on this slide is a representation of what happens to the pressure volume loop when you increase preload. So on the left is the baseline pressure volume loop, and on the right is the pressure volume loop after we've raised the preload. And the first thing you can see is that this point right here, which I told you before represents the end diastolic volume, it's higher on the x-axis in the curve on the right. And that's because we've added more preload. Remember, when the left ventricle fills, it moves along this dotted line along the bottom here. This is called the end diastolic pressure volume relationship. And it moves until it's filled to the point where the mitral valve closes. Well, when we raise preload, it fills more and it reaches a higher end diastolic volume like shown here. You should also be able to appreciate that this red pressure volume loop is wider than the gray one on the left. That means that the stroke volume has increased. And so at the top of the screen, I've summarized the important changes that you should know about pressure volume loops when preload goes up. The end diastolic volume rises from more filling, the stroke volume goes up, and remember, stroke volume is equal to end diastolic volume minus end systolic volume. This is the stroke volume over here. So if end diastolic volume goes up, the stroke volume should go up. And then basically, since stroke volume is in the numerator of the equation for ejection fraction, usually anytime the stroke volume goes up, the ejection fraction goes up too. And that's what happens when you raise the preload. You get a slight increase in the ejection fraction under most circumstances. Shown on this slide is what happens when you decrease preload. It's the opposite of everything on the last slide. You reach a lower end diastolic volume, you have a smaller stroke volume, and the ejection fraction goes down slightly. And all these things you can glean from looking at the pressure volume loop here. Now let's talk about what happens to the pressure volume loop when there's an increase in afterload. So I told you before that this point right here represents the afterload. That's the pressure that has to be generated inside the left ventricular cavity for the aortic valve to open so that blood can start to leave. Well, when the afterload goes up, that point moves higher, as you can see in the red pressure volume loop on the right side of the screen. This means a higher pressure has to be achieved before the aortic valve will open. As a consequence of this point being higher, when blood starts to leave the left ventricular cavity, it hits this dotted line sooner. This dotted line, remember, represents the end systolic pressure-volume relationship. So because it hits that line sooner and then the pressure starts to fall, we have a narrower pressure-volume loop on the right, representing a fall in stroke volume. And if you think about it, that should make sense. When there's more afterload, there are more forces resisting the flow of blood out of the left ventricular cavity, and therefore it's able to push out less blood because the afterload is higher, so the stroke volume falls. Also notice that this point right here is the end systolic volume. We talked about that a few slides ago, and you can see that it moves up along the x-axis to a higher point in the pressure volume loop with high afterload. And that also makes sense when you think about it. If there are more forces resisting the flow of blood out of the left ventricle, then at the end of systole, it won't have pushed out as much blood and the volume will be higher. And so I've summarized these changes at the top of the screen here. The end systolic volume goes up, the stroke volume goes down. And remember what I said, ejection fraction is equal to stroke volume divided by EDV. So when the stroke volume falls, usually the ejection fraction goes in the same direction. And that's what happens here, the ejection fraction falls. And then here on this slide are the changes that occur when you decrease afterload. It's the opposite of everything we talked about on the last slide. Instead of the pressure volume loop getting narrower, it gets wider, and that's because stroke volume is going up. When contractility increases in the left ventricle, it moves the end systolic pressure volume relationship from the dark line here to the red line here. It flips it upwards in this direction. And that changes the pressure volume loop from the gray baseline on the left to the red one on the right side of the screen. The major consequence here that you can see is that the pressure volume loop is wider, so stroke volume has gone up. And that should make sense to you. If contractility goes up, you would expect stroke volume to increase. And because stroke volume has gone up, more blood is pushed out of the left ventricle, so the volume at the end of systole here is going to be lower compared to what it is before. So here's the baseline, and now after contractility goes up, the end systolic volume has fallen. So I've summarized these changes at the top of the screen here. The end systolic volume goes down, the stroke volume goes up. And remember what I said, as stroke volume goes, so does ejection fraction, and so the ejection fraction goes up when you increase contractility. And then here's what happens when you decrease contractility. You move the end systolic pressure-volume relationship in this direction. That creates a narrower pressure-volume loop representing a smaller stroke volume, and the end systolic volume point here has gone up instead of gone down like we saw on the last slide. And so that produces all these changes shown right here, the opposite of what we saw when contractility increased. Now let's talk about how the pressure-volume loop changes when there's a decrease in compliance. In terms of compliance, the only important change to know about for the pressure-volume loop is what happens with a decrease in compliance, because that's what occurs in diastolic heart failure. If you have a stiff, thick ventricle, that ventricle has a low compliance. So compliance dictates the slope of this line here, the end diastolic pressure-volume relationship. It makes this line more steep when there's a decrease in compliance. And so when that happens, you get a pressure-volume loop like the one in red on the right side of the screen here. And the first thing you should notice is that this pressure-volume loop is narrower. And as we've discussed, that always means a fall in stroke volume. And that makes sense when you think about it. When the ventricle is stiff, it can't fill with as much blood because it's stiff and can't relax. And therefore, less blood fills the chamber and less blood leaves the chamber with each cycle, so there's a lower stroke volume. Also notice that this point right here, the end diastolic point, which represents this end diastolic volume point right down here, has fallen compared to what we have at the baseline. That's another consequence of a stiff left ventricle. It can't fill with as much blood, so the volume at the end of diastole is lower. And so I've summarized these changes at the top of the screen here. The end diastolic volume falls, the stroke volume falls, and the ejection fraction falls. Let me make a general comment about the work of the heart. So if you look at these two pressure volume loops, you can tell just from looking at them that this one represents a ventricle doing more work. The bigger the area of the pressure volume loop, the more work the heart is doing. Because the taller the pressure volume loop gets, that's the more pressure being generated, and the wider represents the more volume that it's accommodating. So ventricles that accommodate more volume and generate more pressure require more work. And so you can tell something about the work of the heart just by looking at the size of the pressure volume loop. I'll finish this module by showing you a couple of valvular disease states. These are sometimes shown on board exams, so the rest of this video we'll see an example of what each of them looks like so you can recognize it. So the first one we'll look at is aortic stenosis. On the left side of the screen in gray is a normal pressure volume loop, and on the right side in red is a pressure volume loop with aortic stenosis. And remember what I told you before, this point right here represents the afterload on the left ventricle. In aortic stenosis, there's more afterload. The ventricle has to generate a higher pressure before that stiff aortic valve will open. And that's what you see in the pressure volume loop on the right. The LV systolic pressure rises because of the stiff aortic valve. When the valve finally does open, blood starts to leave the ventricle, but then it hits this end systolic pressure volume relationship line sooner than it otherwise would and starts to go down. And that leads to a narrower stroke volume like you can see here. Remember, the narrower the pressure volume loop, the lower the stroke volume. So that's what happens in aortic stenosis, higher afterload causing a reduction in the stroke volume. Now let's look at aortic regurgitation. So aortic regurgitation changes the pressure volume loop to look like this big red glob over here on the right. And basically what's happening is the isovolumic portions of the pressure volume loop are being disrupted. Remember we talked about how this section right here of the normal pressure volume loop and this section right here are straight lines up and down because volume is not changing. Well, the only way those lines stay straight and volume stays constant is if the two valves work and they can shut. But in aortic regurgitation, you have a leaky aortic valve, so you don't get these isovolumic periods. Instead, you get curved periods like what you see here in the loop on the right. And one of the most important places where aortic regurgitation disrupts the pressure volume loop is in isovolumic relaxation. When the ventricle is trying to relax but keep the volume constant, that aortic valve is leaking and allowing the ventricle to fill with blood. So that causes the isovolumic relaxation section of the PV loop to be curved like what you've got over here on the right side of the screen. So normally at the end of systole and when the mitral valve opens, the volume shouldn't change. But if you look at the top right side of the screen, this is what can happen in aortic regurgitation. At the end of systole, the volume is 40 here. I've made up some numbers to illustrate the point. And by the time the mitral valve opens, the volume has increased because of blood leaking into the ventricle through the aortic valve. On the right side of the screen here is what mitral stenosis looks like compared to a normal pressure volume loop on the left. Basically, it has the same shape and contours of the normal loop. It's just smaller in all regards compared to a normal loop. And that's because less blood can fill the ventricle because there's resistance to flow across the stenotic mitral valve. And I'll finish by showing you mitral regurgitation. So mitral regurgitation changes the pressure volume loop from the normal example on the left side of the screen to this red circular thing on the right side of the screen. And once again, what's happening is you don't have these isovolumic sections of the pressure volume loop because the mitral valve is leaky. For there to be an isovolumic portion of the cardiac cycle, the aortic and mitral valves have to both shut and not allow any blood to enter or leave the ventricle, and that doesn't happen in mitral regurgitation. And the main portion of the pressure volume loop that's disrupted in mitral regurgitation is isovolumic contraction, which becomes curved like it is over here. So remember, the time from the end of diastole down here to when the aortic valve opens, there should be no change in volume, but we do have a change in volume because the mitral valve is leaky. So you could get numbers like what's shown at the top of the screen here. I've done this just to illustrate the point, but at the end of diastole, you could have a volume of 140, but when the aortic valve opens, that volume has decreased to 130, and the reason that it hasn't stayed constant but has gone down is because blood is leaking backwards through the leaky mitral valve. And that concludes our module on pressure volume loops.